Am I audible? Is my screen visible? Can you please unmute and tell me whether the screen is visible? Is my screen visible?
Yes, sir.
Okay, right. Thank you. Good evening to all. Welcome to the 12th week problem solving session of NPTEL course IC Engines and Gas Turbine. My name is Ananthakrishnan. I'm a PhD student from IIT Delhi. I do this problem solving session as part of my PMRF TA duty. This is the last week of a problem solving session. So in this week, we will be covering, we'll be revising the topics which we have seen in the previous 11 weeks. And we will be definitely we'll be covering up a lot of portions which we have seen initially. And this will be a good exercise for you before the exam. Without wasting much time, we can go to the questions. So kindly look into the problem. I'll give you 1 minute to look into it, and later I will try to explain it. So in the question it's been mentioned, it's a 6-cylinder 4-stroke CA engine. It has got a 10 centimeter diameter. The cylinder has got 10 centimeter diameter and 12 centimeter stroke. It runs at 2000 RPM. The compression ratio for the CA engine is 18. The engine is connected to a dynamometer, giving a brake output torque reading of 300 Newton meter. Air enters the cylinder at 0.9 bar and 39 degrees Celsius. And the mechanical efficiency of the engine is 85%. The engine runs with an air-fuel ratio of 20. The heating value of the fuel is 42,000 kilojoule per kilogram. Combustion efficiency is 98%. The standard density of the air is 1.181 kilogram per meter cube. We need to calculate the brake power, indicated power, brake mean effective pressure, indicator mean effective pressure, friction mean effective pressure, power loss to friction, brake work per unit mass of air in the cylinder, brake specific power, brake output per displacement, engine specific volume, rate of fuel flow into the engine, brake thermal efficiency, and indicator thermal efficiency, volumetric efficiency, and brake specific fuel consumption. So this is a problem which comprises of almost everything which we have learned in the fundamentals of IC engines. So solving this problem will give you an idea regarding the fundamentals. Let us start solving this problem. Brake power is given by the formula 2 pi nt divided by 16, where T is the torque, engine torque, N is the RPM. So in this particular problem, it's given us RPM is given 2300, torque is 300 Newton meter, and yeah, so solving this will get brake power to be 62.83 kilowatt. Second one, we need to calculate the indicated power. So in indicated power, the indicated power can be related to the brake power by using the mechanical efficiency of the engine. So mechanical efficiency is actually the brake power divided by the indicated power. So indicated power is equal to the brake power divided by mechanical efficiency. So 62.83 divided by mechanical efficiency is 0.85. So the value will be 73.92 kilowatt. The next one, we need to calculate the brake mean effective pressure. Brake mean effective pressure and brake power are related by brake power BP is equal to brake mean effective pressure into length of stroke into area of the bore cross section into number of RPM divided by 60.
Okay. Sir, indicated power equal to होता है sir.
What?
Sir, indicative power equal to होता है sir. P mean pressure, mean active length and to K.
Yeah, actually, in order to calculate the brake power, we can use the same brake mean effective pressure. So in this question, it's been asked, we need to calculate the brake mean effective pressure. So brake mean effective pressure will be related to the brake power using the similar equation as that of the indicator mean power and indicator power.
Oh, thank you. Sorry, sir.
Right. So this is a 4-stroke engine. So it will be we will be getting number of RPM, the number of cycle per second will be equal to number of RPM divided by 2. So we have to multiply n divided by 60 into 1 by 2. And this is for the brake power indicator brake. The brake power is for all the 6 cylinders combined together. This is a 6-cylinder engine. So we have to divide the no, actually the brake power we need to calculate for the 6-cylinder I beg your pardon, 6 cylinders together. So this brake power value
Into K, sir. Six cylinder
yeah,
equal to
into
K.
6, right? Into 6, right? So the whole brake power will be given for all the 6 cylinders together. So we have to multiply it. We have to multiply it by 6. So from this we can calculate the mean pressure, the mean effective brake pressure. So this is brake mean effective pressure is equal to 120 into Bp divided by LAN into 6. So it will be 120 into brake power. We have already calculated it to be 62.83 kilowatt divided by length. In this given problem, length is given as 12 centimeter, that is 0.12 meters. Bore is 10 centimeters, so the area of the cross section will be pi by 4 into 0.1 square. A number of RPM is equal to 2000. So we have divided by 2. That's why the top numerator has got 120, the value 120. And the brake power calculated is for the 6 cylinders together. So that's why we have multiplied it by 6. For a single cylinder, this quantity should be divided. This quantity will be brake mean effective pressure into N by 60 into 1 by 2 is for a single cylinder. So 2000, 6. So the quantity will be coming around
2000 की 12,000.
2000.
1200 and speed, sir.
Excuse me. Yeah. Could you be a bit more audible? 2000.
Yes, sir. Speed n sir. Speed कितना है sir? 2000 sir. 1200.
Yeah. Speed is 2000 RPM. So we have to divide it by 2. That 2 we have multiplied on the numerator. That's why this 60 become 120 for the number of cycles per second. So the value will be coming around 6.65. 6.675 bar. Similarly, the indicated power just like indicated power is related to the brake power by mechanical efficiency, indicated mean effective pressure is related to the brake mean effective pressure by the mechanical efficiency. As a right hand side remains a term, as a right hand side remains the same for this quantity ln by 60 into 1 by 2 remains the same for both the brake power, brake mean effective pressure relation, as well as the indicator power, indicator mean effective pressure relation. So the same ratio, the proportionality constant between the brake power and the indicator power holds true between the brake mean effective pressure as well as the indicator mean effective pressure, and that proportionality constant is the mechanical efficiency. So we can write it to be 0.85, so it will be coming around 7.85 bar. So in this problem, we have calculated the brake power, indicator power, brake mean effective pressure, indicator mean effective pressure. Now we have to calculate the friction mean effective pressure, frictional power. The next quantity will be that. So the friction mean effective pressure FMAP is the difference between indicator mean effective pressure and the brake mean effective pressure. So it will be 7.85 minus 6.67 equal to 1.18 bar. 1.18 bar. Similarly, the frictional power FP is equal to the indicated power minus brake power. It will be 73.92 minus 62.83. That will be coming around 11.09 kilowatt. Now we need to calculate the next quantity. Frictional mean effective pressure calculated and power loss to friction is also calculated. We need to calculate the brake work per unit mass of air in the cylinder. We need to calculate the brake work per unit mass of air in the cylinder. So the unit will be kilojoule per kilogram. We need to calculate this quantity. So in this one, first of all, we need to calculate the brake work per cylinder in one cycle. So that we can calculate by brake mean effective pressure.
सर लाइक कर रहा है.
हाँ
सर आपका ऑडियो से बोर्ड पे लिख रहे हैं तो दिख रहा नहीं, बाद में दिख रहा है लिखा हुआ।
What?
सर आप लिख
Hello?
रहे हैं सर तो दिख नहीं रहा, एक बार पूरा लिखा हुआ दिख रहा है सर। लैग कर रहा है थोड़ा थोड़ा सर, आपका आवाज भी
Is it not visible? The slide not visible?
सर।
No, can you please write it in the chat box? I couldn't hear your voice properly.
अब ठीक है सर, आप कंटिन्यू करें सर, प्रॉब्लम हो तो चैट कर दें।
Yeah. The brake work per cylinder per cycle is given as the product of the brake mean effective pressure as well as the stroke volume. So it will be coming around will be coming around 0.629 kilojoule. Now we need to calculate the brake work per unit mass of air in the cylinder. We have calculated the brake work per cylinder per cycle. Now we need to calculate the brake work per unit mass of air. So this quantity should be divided by the mass of air in one cylinder per cycle. So how to calculate the mass of air per cylinder per cycle? MA is equal to pressure into the total cylinder volume. The total cylinder volume will be equal to the volume at the bottom dead center divided by R into T. So this quantity is an unknown quantity. Pressure is given in this problem as 0.9 bar. Air enters the cylinder at 0.9 bar and 39 degrees Celsius. So we know temperature, pressure, R value we know. We have to calculate the volume at the bottom dead center. So VBDC is equal to V total equal to V clearance plus V stroke volume. So the clearance volume is equal to the stroke volume divided by compression ratio RC minus 1, because compression ratio is the product of the total volume divided by the clearance volume. So from that we can get this value, clearance volume is equal to stroke volume divided by compression ratio minus 1 plus stroke volume. That will be giving the total volume. So it will be coming around the stroke volume we need to calculate. The stroke volume is equal to the pi by 4 into d squared into L quantity. The stroke volume or the swept volume equal to pi by 4 into d squared into L. So pi by 4 into 0.1 squared into 0.12. Equal to, it will be coming around 0.9969 10 power minus 3 0.9969 into 10 power minus 3 meter cube. So substituting this value here will get the volume, total volume is equal to so I beg your pardon, there is a slight correction. The value will be coming, the swept volume. There's a slight correction in the value. It will be coming around 0.9424 into 10 power minus 3 meter cube. So the total volume, the total volume will be equal to Vs divided by gamma minus 1 plus Vs. So substituting the value of Vs in this one, we'll get the value to be equal to 0.0554 plus 0.9424 into 10 power minus 3. That will be coming around 0.9969 into 10 power minus 3. So we have calculated the swept total volume. That is a volume at the BDC is equal to 0.9969 into 10 power minus 3. Pressure is equal to 0.9 bar, 0.9 into 10 power 5 into 0.9969 into 10 power minus 3 divided by R value is 287 into temperature is 39 degrees Celsius. That in Kelvin it will be coming around 312. So the answer will be coming around 1.002 into 10 power minus 3 kg. Therefore, brake specific work per unit mass work per unit mass of air is given by so this quantity will be 0.629 divided by 1.002 into 10 power minus 3. It will be coming around 628 kilojoule per kilogram. So the brake specific work per unit mass of air is the product is the ratio of the brake specific work, brake power per the brake work per cylinder per cycle divided by the mass of air per cylinder per cycle. So we have calculated the brake work per unit mass of air in the cylinder. The next we need to calculate the brake specific power. So brake specific power is the brake power per unit area. Keep in mind it is specific power. Brake specific power, it's different from the other quantity. So it's the brake power divided by the area of the piston, cross-sectional area of the piston. So it will be coming SP is equal to brake power divided by AP. So brake power we have already calculated. The area of the piston is equal to 5/4 into d squared So this brake power we have calculated for 6 cylinders together. So for a single cylinder, brake specific power will be brake power divided by number of cylinders divided by pi by 4 d squared. So it will be coming around 62.83 divided by pi by 4 into 0.1 squared into number of cylinders is 6. So the quantity will be coming around 1333 units kilowatt per meter squared. 1333 kilowatt per meter squared. The unit of brake specific work per unit mass of air is kilojoule per kilogram. Right. So we have calculated the brake work per unit mass of air in the cylinder and the brake specific fuel power. Now we need to calculate the brake output per displacement and the engine specific volume, rate of fuel flow into the engine, brake thermal efficiency, indicator thermal efficiency, volumetric efficiency, and brake specific fuel consumption. So the brake output per displacement, it's a ratio of the brake power divided by the stroke volume. So the brake power given in this particular problem will be 62.83 kilowatt for 6 cylinders. So per cylinder it will be 62.83 divided by 6, and we have to calculate the volume, the stroke volume. So it will be coming around 0.94. We have calculated the stroke volume to be 0.9424 into 10 power minus 3 meter cube. So the brake output per displacement, the unit of that quantity will be equal to kilowatt per meter cube. So that will be coming around output brake output per displacement OPD is equal to brake power divided by the stroke brake power for the 6 cylinders divided by the stroke volume or the sweat volume multiplied or per cylinder multiplied by number of cylinders. So that will be coming around 11.1 into 10 power 3 kilowatt per meter cube. Brake output per displacement, the unit will be kilowatt per meter cube. The next one we have to calculate the engine specific volume. Engine specific volume will be the reciprocal of brake output per displacement. So the engine specific volume equal to Vs total, that is Vs into number of cylinders divided by the brake power of 6 cylinders together. So this will be equal to 1 by reciprocal of, it's a reciprocal of a brake output per displacement 11.11 into 10 cube 0.09 into 10 power minus 3 meter cube per kilowatt. So in this particular problem, we need to calculate the next quantity, the rate of fuel flow into the engine. So in this given problem, the air fuel ratio is given as 20. Mass of fuel in one cylinder per cycle is equal to mass of air divided by 20, and we can calculate the mass flow rate of fuel. And then the rate of fuel into the engine is given by the mass flow rate multiplied by number of cycle per second multiplied by the number of cylinders. So the rate of fuel in nutshell, we can express it to be air fuel ratio is equal to 12. Therefore, mass of air divided by mass of fuel is equal to 20. Air fuel ratio is 20. So the mass of fuel in one cylinder per cycle equal to mass flow rate of 20. The mass, there is no dot sign. It's pure mass term, not a rate. We have calculated the mass flow rate of air to be 1.022 into 10 raised to minus 3 divided by 20. So we have calculated the mass flow rate of fuel. We need to calculate the rate of fuel into the engine. So this needs to be divided by the second time quantity. So indirectly it can be calculated as mass flow rate of mass flow into the now RPS, revolution per the cycle per second. So 120, 2 is for the four-stroke engines. Into this is a revolution per second. This is kilogram. This is cycle per second, and we need to multiply it by the quantity. So this is per cylinder. So this quantity is per cylinder. We need to multiply it by the number of cylinders. This will be equal to kilogram for the number of cycles, the total mass flow rate per cylinder. So we need to multiply it by the number of cylinders to get the total mass flow rate into the engine. So this is 0.05 per cylinder. Per RPM. So we need to multiply it by the RPM per second multiplied by the cycle will be giving. This is 0.0501 cycle per kilogram per cycle. This kilogram per cycle. This is cycle per second. and this is the number of cylinders. This whole quantity is per cylinder quantity, and we need to multiply it by the number of cylinders. So this will be coming around from the airflow rate. We can calculate airflow rate and the mass of air per cycle. We can calculate the mass of fuel per cycle multiplied by the number of cycles per second will be giving the mass flow rate per cylinder per second multiplied by the number of cylinders, we'll be getting the mass flow rate of the fuel into the engine in terms of kilogram per second. Then we need to calculate the brake thermal efficiency and indicator thermal efficiency. Brake thermal efficiency, brake power divided by the mass flow rate of fuel to calorific value, mass flow rate of fuel in terms of kilogram per second. That's obtained by mass flow rate of the fuel, mass flow rate of the fuel per cylinder multiplied by number of cylinders. So the mass flow rate per cylinder is obtained by mass flow rate mass per cycle multiplied by the number of cycles per second. Since it's a 4-stroke engine, the number of cycles per second will be equal to half of the number of revolutions per second. So this value will be equal to its value will be coming to be around huh?
42,000, sir. Electric value 42,000.
Right. Divided by 0.00501. This is this quantity multiplied by CV, and the in normal terms, when there is no combustion efficiency, we can directly take the input energy to be equal to mass flow rate into the calorific value of the fuel. But since combustion efficiency of 0.98 is given, so input energy to the engine will also be reduced by that factor. So this is the combustion efficiency, intercombustion. So it will be coming around, this is 42,000 multiplied by 0.98. So it will be coming around 0.305. So efficiency will be 30.5%. Brake thermal efficiency. The indicated thermal efficiency is related just like the indicator power to the power or indicated mean effective pressure to the brake mean effective pressure. Indicated thermal efficiency is related to the indicated brake thermal efficiency by the mechanical efficiency term. Indicated thermal efficiency, is related to the indicated brake mean efficiency, brake thermal efficiency. Beg your pardon, brake thermal efficiency divided by the mechanical efficiency of the engine. So it will be coming around 30.5, 0.305 divided by the mechanical efficiency will be 0.85. So the answer will be 35.9%. So that will be the indicator thermal efficiency. We can calculate it from the brake thermal efficiency. So we have calculated the brake thermal efficiency. We have calculated the indicator thermal efficiency. Now we need to calculate the volumetric efficiency and the brake specific fuel consumption. So earlier we have calculated the brake power, brake output per displacement. So the engine specific volume will be in reciprocal of the brake output per displacement. So the engine specific volume we have calculated it to be in terms of meter cube per kilowatt. Next, we need to calculate the volumetric efficiency and the brake specific fuel consumption. The brake specific fuel consumption will be in terms of kilogram per kilowatt hour, the energy, kilogram divided by the energy. Volumetric efficiency, before that, we need to calculate the volumetric efficiency. Eta volume is equal to the mass flow rate the mass of air that is calculated as 1.002 per cylinder per cycle. 1.002 into 10 power minus 3 kg divided by density into stroke volume. So it will be coming around standard density of air is given as 1.181 kilogram per meter cube. So the mass of air per cylinder per cycle is given as 1.002 into 10 power minus 3 divided by 1.181 into it's coming around 0.9. So the volumetric efficiency is the actual mass flow rate of air, mass of air to the theoretical maximum air entering the engine. And the last quantity is brake specific fuel consumption. TSFC equal to the mass flow rate of a fuel divided by the brake power, while the engine specific volume will be the volume flow rate divided by the power, the volume flow rate of air. Engine specific volume will be the reciprocal of the brake output per displacement. It's a the ratio of the total volume divided by the brake power produced. So here brake specific fuel consumption is the mass of the fuel, mass flow rate of the fuel to the engine divided by the total brake power. The previous analysis, it was the volume for the brake power per cylinder analysis. So here it will be mass flow rate of the fuel in cylinder per cycle is given as 0.0501 into 10 power minus 3. Mass flow rate of the fuel taking into consideration the 4-stroke engine and the 6 cylinders engine, the total mass flow rate of the fuel is equal to 0.0501 divided by the brake power. So this quantity is kilogram per second. Brake power will get as 62.83. Kilo. If you want to calculate the value in terms of kilogram per kilowatt hour, we need to divide the quantity by the multiply the numerator by 3600. So it will be coming around this quantity was kilowatt, 62.83 kilowatt. So in order to convert that particular quantity into kilowatt hour, we have multiplied it with the 3600 on the numerator and the denominator. So it will be coming around this new denominator will be coming around. It's in terms of kilowatt hour, and the quantity total quantity will be 0.287 kilogram per kilowatt hour. So we have calculated the engine specific volume ESV, and now we have calculated the brake specific fuel consumption, where the mass flow rate of the fuel into the engine will be divided by the total brake power that is achievable from all cylinders put together. So its unit is kilogram per kilowatt hour brake specific fuel consumption. We multiply the denominator and the numerator by 3600. So we'll be getting it in terms of kilogram per kilowatt hour. So that completes the first problem, where we have seen almost all the basic fundamentals of IC engines. We have calculated almost all important parameters in this problem. So now we can move to the second problem. In an air standard diesel engine, the compression ratio is 60. The cylinder bore is 200 millimeters and the stroke is 300 mm. Compression begins at 1 bar and 27 degrees Celsius. The cutoff takes place at 8% of the stroke volume. We need to calculate the pressure, the volume, and the temperatures at all important points, the cutoff ratio, the work done per cycle, the air standard efficiency, and the mean effective pressure. So in this particular problem, first of all, we draw that PV diagram. That's a diesel air standard diesel cycle. So in this PV diagram, constant pressure heat addition process and the constant volume heat rejection process. The diameter D is given as 0.2 meters, 200 mm. Stroke is 300 mm, 0.3 meters. Compression begins at 1 bar and 27 degrees Celsius. The cutoff takes place at 8% of the stroke volume. So V3 minus V2 is equal to 8% of Vs. And we can write it straight away. V3 minus V2 is equal to 0.08 times of V stroke. Compression ratio RC is equal to 16. We need to calculate the pressure and the volume and the temperature at all important points. First of all, we need to calculate the swept volume. And from the swept volume, we can, based on the compression ratio, we can calculate the clearance volume. And using the clearance volume and the cutoff ratio, we can calculate the cutoff volume. And using all these parameters, we can calculate the pressures and the corresponding temperatures. So in this particular problem, we need to calculate the pressures, temperatures at the end of the compression. So pressures, temperatures, volumes at the beginning and the end of the compression. So that will be solving the first problem. The second problem, we need to calculate the cutoff ratio. And then
cutoff ratio 0.2 आया है.
how much?
0.2.
Cutoff ratio. Cutoff ratio is not a straightforward. Cutoff ratio is V3 by V2. It will check once again what will be the cutoff ratio. So V3 by V2 will be greater than 1, right? It will be somewhere around 2.2. Check once again. So I'll try solving this.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. No, manage this.
Right. So in this particular problem, first of all, we start by calculating the swept volume. Equal to 5 by 4 into 4 squared into length equal to 5 by 4 into 0.2 squared into 0.3, 200 mm and 300 mm respectively. So it will be coming around 0.00942 meter squared. In this particular problem, the compression ratio R is given as 16. That is equal to V1 divided by V2 is equal to V stroke plus V2 for the clearance volume divided by Vc is equal to 16. That is Vs divided by Vc plus 1 is equal to 16. So Vs by Vc is equal to 15. The stroke volume divided by the clearance volume is equal to 15. So the stroke volume of the swept volume is equal to 0.00942. Therefore, the clearance volume Vc is equal to, in this PV diagram, it is V2 is equal to Vs divided by 15. That will be coming around 0.000628 meter cube, meter cube. And then we can calculate the volume at start of the compression. V1 is equal to Vs plus Vc. So that will be equal to 0.000628 plus 0.00942. That will be coming around Vc plus Vc. That will be coming around 0.010048 meter cube. And then we need to calculate the mass flow rate of air at the start of the mass of air per cylinder at the start of the compression. So that can be calculated by the formula PV by RT, considering air to be an ideal gas. Then start of the compression is at 1 bar and 27 degrees Celsius. So in this particular problem, P1 is equal to 1 bar, P1 is equal to 227 degrees Celsius over 300 Kelvin. So P2 we can calculate to be it's a reversible adiabatic isotropic compression. So P2 is equal to P1 into V1 divided by V2 raised to gamma. So P1 is 1 bar. So V1 by V2 raised to gamma will be giving the gamma for air can be assumed to be 1.4. Will be coming around 48.5 bar. 2 to 3 is a constant pressure process. So P3 equal to P2 is equal to 48.5 bar. T2 equal to P1 into P2 by P1 raised to gamma minus 1. So T2, the temperature at the end of compression is equal to T1 300 into P2 by P1 raised to gamma minus 1.
909.
Right. 909.4 Kelvin. Now we need to calculate the second portion. So we have calculated the pressures and temperatures and volume at the beginning and the end of the compression. The cutoff ratio we need to calculate, and based on that we have to calculate the work done per cycle, the air standard efficiency, the mean effective pressure. The cutoff ratio
to 909.42, sir.
how much?
909.
Cutoff ratio. Yeah, the quantity temperature T2 was 909. We need to calculate the cutoff ratio. The cutoff ratio Theta is equal to V3 divided by V2. V3 by V2. Given V3 minus V2, V3 minus V2 is equal to 0.08 into V4. That implies V3 by V2 minus 1 is equal to 0.08 Vs divided by V2. Vs by V2, Vs by V2, that is stroke volume divided by clearance volume. So that will be equal to 0.08 into compression ratio minus 1. So therefore, V3 by V2 V3 by V2 equal to 1 plus 0.08 into RC. RC is 16. So RC minus 1 is 15. So it will be coming around 2.2. The clearance volume we calculated the cutoff ratio using the cutoff clearance volume as well as the clearance volume as well as the cutoff volume. Next, we calculate the other pressures. Since till now we have calculated the pressures, temperatures at the exit of the compressor. At the exit of the heat addition, we have calculated the pressure. But now, since we have got the cutoff ratio, we can calculate the temperature at the exit of the heat addition, constant pressure heat addition process. So we can calculate V3 equal to V3 equal to beta times V2. To V2, we know the value we have calculated it to be 0.000628. So V3 cutoff volume will be equal to 0.001382 meter cube. Therefore, T3 we can calculate T3 constant pressure process is equal to beta into T2. Temperature directly proportional to the volume. So T1 by V1 is equal to T2 by V2. So it will be coming around T2 temperature at the exit. We have calculated it to be 909.4 Kelvin. So the peak temperature in the process will be 2001 Kelvin. Therefore, the P3 temperature, the pressure at the exit of the pressure at the exit of the heat addition process will be same as that of the pressure before it, since it's a constant pressure process. So we can calculate we know the value of V3, V4 will be same as that of V1. V4 volume will be same as that of V1. So we also have calculated V3. We know the value of P3, we can calculate P4 as well as P4. So the P4 value will be equal to P3 into V3 by V4, the whole raised to gamma is equal to P3 into V3 by V2 into V2 by V1, the whole power gamma. V3 into V3 by V2 is equal to cut-off ratio. V1 by V2 is equal to compression ratio. The whole power gamma is 1.4. So 48.5 into 22. So it will be coming around 3.016 bar. That will be the cutoff ratio to get the final pressure value at the exit of the expansion process. From this one, we can calculate the T4. T4 is equal to T3 into T3, the peak temperature in this process, we have calculated it to be 2001 Kelvin. So beta is given as 22 and 2.2 and RC is equal to 2. We have calculated the temperature at the exit. Now V4 will be same as that of V1 is equal to 0.010048 meter cube. Then we need to calculate, we have got the temperatures, pressures at each and every points. So we have achieved the first objective and we have achieved the second objective in this meantime and the work done per cycle. So we need to calculate the work done per cycle. Work done per cycle will be equal to heat rejected, heat supplied minus heat rejected. So it will be Q23 minus Q41. Work done per cycle. W is equal to Q1 minus Q2. This is the heat supply. It's an air standard cycle, so hence we haven't calculated the mass flow rate of a fuel, but it's actually mass of air in terms of kilogram. So this mass of air we can calculate by this quantity 0.01167. It we can calculate by P1, the standard ideal gas equation P P by P1 is V1. So this equation we can calculate. It can be used to calculate the mass flow rate of air to be around a 0.01167. So volume divided by 287 into 300. So it will be coming around 0.01167 kilogram. So we have calculated the mass flow rate. The mass, rather than mass flow rate, it's a mass of air. So the air standard efficiency can be calculated at for the air standard diesel cycle. As the work produced divided by the heat input, the work done per cycle. Work done per cycle we have calculated as 7.732, and the work input is equal to 12.8. So it will be coming around 0.604. 60.4% will be the efficiency. And then we have to calculate the mean effective pressure. PM is equal to work done divided by the stroke volume. So work done will be 7.732 into 10 cube divided by the swept volume or the stroke volume will be 0.00942. This is the work done per cylinder per cycle. So it doesn't require the correction factors which we have used in the previous problem to convert from our revolution per second to the cycle per second, where we divide it by 2. Here it is not required since it's per cylinder. It's a kg value per cylinder. It's a volume value per cylinder. So the mean effective pressure will be 8.21 bar. So in this particular problem, we have calculated the pressure, temperature, and the volume at all the important points 1, 2, 3, 4. We have calculated the cutoff ratio, that is V3 by V2. We have calculated the work done per cycle, the air standard efficiency, as well as the mean effective pressure. The next we calculate it's a simple jet carburetor problem. A simple jet carburetor is required to supply 5 kg of air per minute and 0.4 kg per minute of fuel of density 780 kg per meter cube. The air is initially at 1.013 bar and 27 degrees Celsius. Calculate the throat diameter of the choke for an air velocity of 90 meter per second. Take the velocity coefficient for the venturi to be 0.8 and the main fuel jet's discharge coefficient to be 0.6. Assume isentropic flow and the flow to be compressible. If the pressure drop across the fuel metering orifice is 0.75 of that at the top. Calculate the orifice diameter. So in this particular problem, this is a case of a carburetor. So this will be the schematic of a carburetor. This is the inlet point, ambient condition. Air comes in, and this is the choke point of least area for travel. And then at this particular point, the fuel is being delivered from the fuel tank, and the fuel air mixture combined will be coming out of the carburetor. So in this model, the mass flow rate is of air is 5 kg per minute. Mass flow rate of fuel is 0.4 kg per minute. And the starting pressure P1 is equal to 1.013 bar. T1 is equal to 300 Kelvin. The pressure and temperature at the starting point. The velocity C2 at the choke point is 90 meters per second. Venturi coefficient will be 0.8. Discharge coefficient of the fuel will be 0.6. After applying the steady flow energy equation across 1 and 2, we get H1 plus C1 squared divided by 2 is equal to H2 plus C2 squared by 2. Initially, it will be at 0 velocity. So we can calculate compared to choke velocity, the velocity at the choke, velocity at the inlet will be negligible. So H2 is equal to H1, H2 minus H1. So H1 minus H2 is equal to C2 squared by 2. So we calculate the actual velocity of air at the point 2. C2 from this one will be equal to 2 Cp into T1 minus T2 can be written as 2 Cp T1 into 1 minus T2 by T1. In terms of pressure, it can be written as 2 Cp T1. It's an isentropic process. So isentropic process, it can be written as P2 by P1 into gamma minus 1 divided by gamma. So C2 can be written in terms of CV. So this is the velocity C2, which we get from the steady flow energy analysis. But in this given problem, the the Venturi coefficient at point 2 is given to be 0.8. So the actual velocity will be actual velocity of air at a plane 2 C2 actual equal to Cv into 2Cp into T1 into 1 minus P2 by P1 raised to gamma minus 1 divided by gamma. In this particular problem, we need to calculate the pressure. We need to calculate the orifice diameter. So the actual velocity is given as 90 meter per second. So actual velocity 90 meter per second is equal to discharge coefficient 0.8 into 2Cp into T1. The quantity temp T1 is equal to 300 Kelvin. Into 1 minus P2 by P1 into gamma minus 1 divided by gamma. So it will be coming around 8000 divided by 0.8 into 0.8 equal to 2Cp into Cp value is equal to 1.01005. So we can substitute it to be 2 into 1005 into 300 into 1 minus P2 divided by P1 is 1.013 bar is to gamma minus 1 divided by gamma. So solving this, we'll get P2 is equal to 0.9405 bar. So pressure slightly reduced inside the choke compared to the intake to the carburetor. Intake to the carburetor was at the atmospheric pressure, so the choke will be at a slightly lower pressure for air intake. This is the throat pressure. The actual velocity at the throat is given. From the steady flow energy analysis, we can get the ideal velocity, and we can relate both of them using the discharge coefficient at the throat. The throat pressure is equal to 0.9405 bar. Now we need to calculate the diameter of the throat. So the diameter of the throat, for the calculation of the diameter of the throat, we need to know the area. Area at the throat. And if we know the area, we can calculate orifice diameter. So we will try to solve the second part of the problem. In this problem, we need to calculate the density air at first point is equal to P1 divided by RT1 is equal to 1.013 into 10 power 5 divided by 287 into 300. So it will be coming around 1.1177 kilogram per meter cube. For isentropy flow, P1 by rho raised to PV raised to gamma is a constant, so equivalent to the velocity volume, it's a density. So P2 by rho 2 raised to gamma. So density at the throat is equal to rho 1 into P2 by P1, the whole raised to 1 by gamma, equal to 1.177 into 0.9405 divided by 1.013 equal to 1.16 kilogram per meter cube. In order to calculate the throat area, we apply the continuity equation. The mass flow rate of the air we have calculated. It is given the problem as 5 kg per minute. So at the throat area, mass flow rate is equal to rho 2 into A2 into C2. A2 is equal to mass flow rate divided by rho 2 C2. It will be coming around 5 kilogram per minute. That is 5 by 60 kilogram per second. Rho 2 is 1.116 into C2 is given us this problem was 90. So we'll get A2 is equal to 8.297 into 10 power minus 4 meters square. So this A2 is equal to 5 by 4 into D2 squared. So for calculating D2, the diameter of the throat will be equal to 3.25 centimeters. So we have calculated the diameter of the throat from the mass flow rate of the air. But the next is part of this question, we need to calculate the orifice diameter. Orifice the diameter through which the fuel comes to the carburetor. So in this particular problem, the pressure drop is pressure drop across the fuel metering of orifice is given to be 0.75 at the choke. So the value of the pressure drop at the pressure drop across the fuel metering orifice is 0.75 times that at the choke. So the pressure drop, we need to calculate the pressure drop in the Venturi. So pressure drop in the Venturi, delta P is equal to 1.013 minus 0.94. That will be equal to 0.0725 bar. That will be the pressure drop in the Venturi. So the pressure drop across the fuel metering orifice, the jet is equal to 0.75 times delta P Venturi. So 0.75 times 0.0725. So it will be coming around 0.0544 bar will be the pressure drop across the jet, fuel jet. So the mass flow rate of fuel can be written as for the Venturi meter analysis. So for the orifice analysis. So this coefficient of discharge of the fuel flow into area of the fuel flowing orifice into the velocity. Velocity is equal to root of 2 into the into delta P. So it will be equal to minus of Z into of void. Since Z is equal to 0 in this problem, we can neglect this. So CDF is equal to root of 2GH. So this H head constant, the head value can be written as delta P divided by rho G. So the answer will be coming around we need to calculate the area of the orifice new root of Q rho F into delta P. So the AF is equal to mass flow rate of actual mass flow rate of the fuel divided by CDF into root of 2 into rho F into delta P. So the mass flow rate is given as 0.4 into kilogram per minute, 0.4 divided by 60 kilogram per minute second. So CDF is equal to 0.6 into root of 2 into density of the fuel is 780 kilogram per meter cube into delta P. Pressure drop across the jet is 0.75 times the pressure drop in the injury. It will be 0.0544 into 10 raised to 5. So the answer will be the 3.814 millimeter squared. So the pi by 4 d is equal to 3.814. That implies the diameter of the orifice df is equal to 2.2 millimeter. So we have calculated the this particular problem. In order to calculate the diameter of the orifice, we needed the mass flow rate through the orifice, and the mass flow rate of the orifice. We needed the velocity of the fuel through the orifice. For calculating the velocity, we have calculated the pressure drop through the orifice. That is given as a function of the pressure drop across the venturi. So in order to calculate the pressure drop across the venturi, we had in order to calculate the pressure drop across the venturi, we needed to calculate the pressure at the venturi. So pressure at the venturi, we have calculated based on the isentropic flow and also the isentropic flow. So also the pressure, the density and the pressure are related by the isentropic flow equations. And the pressure at the venturi is calculated from the pressure at the beginning using the steady flow energy equation as well as the venturi coefficient. So this solves the numericals. Next, we'll look into a few multiple choice questions. Abnormal combustion in an SI engine causes high ratio of energy decrease, excessive rise in pressure and temperature, reduction in thermal efficiency, all of the above. So the answer is all of the above. The efficiency of the engine goes down because the compression ratio has to be reduced in order to limit the temperature and pressure of the gas. So in the case of abnormal combustion, it has got a reduced thermal efficiency because the compression ratio has to be reduced to limit the temperature and pressure of the end gas. Because of the presence of the abnormal combustion, there will be the temperature and the pressure. Because of the presence of this abnormal combustion, the temperature and the pressure increases inside the cylinder. The compression ratio has to be reduced to limit the temperature and pressure of the end gas, and also it has got a comparatively lesser. It has got a comparatively high ratio of energy decrease. So what happens is that because of a high temperature in the cylinder, pre-ignition occurs, which result in loss of energy. So abnormal combustion, there is a high ratio of energy decrease. There's a significantly high rise in significant rise in pressure and temperature, and there is a reduction in thermal efficiency because of energy losses. And the compression ratio has to be reduced in order to limit the temperature and pressure of the end gas. Which of the following is correct? An increase in temperature of the combustion chamber of the SI engine decreases the tendency of knocking. An increase in the power output of the SI engine decreases the tendency of knocking. Increase in compression ratio decreases the knocking tendency of the SI engine. Increase in compression ratio increases the knocking tendency of the SI engine. The answer is the increase in compression ratio increases the knocking tendency of the SI engine. So what happens is that the pressure and the temperature at the end of compression increases with the increase in compression ratio. Thus, what happens is that maximum pressure during the combustion, because of this increase in compression ratio, chances of pre-ignition is there for the far away air fuel mixture, which is at a distance from the incoming flame. So increase in compression ratio that increases the knocking tendency in the case of SI engine because of an overall increase in temperature and pressure. Knocking takes place in compression ignition engine at the start of combustion, at the end of combustion, during combustion, at the start as well as at the end of the combustion. So the knocking phenomenon takes place in compression ignition engine at the start of combustion. The ignition delay period or the delay period in a diesel engine is defined as the time interval between the injection of the fuel and the start of the combustion. So the pressure reached during the second stage of combustion is dependent on the duration of delay period. More the delay period, it leads to much more increase in pressure, and this rises the pressure as well as temperature, giving chance of knocking or pre-ignition. Abnormal combustion. So knocking takes place at the start of combustion. The difference with the SA engine is that in SA engine, the knocking happens at the end of the combustion, towards the end of the combustion. At a higher temperature and pressure, the far away air fuel mixture gets pre-ignited before the flame reaches it. But in the case of CA engine, compression ignition engine, the knocking occurs at the start of the combustion. The delay period increases, fuel accumulates more, detonates, pressure increases, detonates at the beginning of combustion. And another difference is that in the case of SA engines, since the air fuel mixture is a homogeneous mixture, the rising pressure will be significant during the time of knocking. But in the case of a CA engine, since the air fuel is a heterogeneous mixture, the rising pressure will be not that much high during the knocking compared to that of the SA engine. But the maximum pressure in the CA engine will be 1.3 to 1.4 times of maximum pressure in SA engine. But during the time of SA engine, the rising pressure will be significant compared to the CA engine due to the difference between homogeneous and heterogeneous mixture. Which is the best option to avoid knock in SA engine? That means that the flame should reach the end charges quickly. So the answer to this problem is increase in engine speed. So to avoid knocking, in SA engine speed has to be advanced. Engine speed has to be increased. What happens if spark is advanced? When the spark is advanced, burning gas is compressed by the rising piston, and therefore temperature and pressure are increased. Thus the tendency of knocking increases. So if you advance the spark, by the time the piston comes to the top dead center, during the time of compression, it gets burned, and there will be a sudden rise in temperature and pressure throughout the air fuel mixture, and because of that there is a chance of the far away mixture getting pre-ignited before the flames reaching them. So spark advance spark before piston reaches top dead center, pressure and temperature increases, chances of pre-ignition percent of the far away air fuel mixture. And the next one is that supercharging low delay period. So in the case of SA engine, there is no delay. So it can be due to the atomization, physical delay, which we might see for the air to atomize and get mixed with the fuel. So in the case of CA engine, since it's an injection fuel injection engine, the atomization physical delays will be present. But SA engines, it's a homogeneous mixture of air fuel mixed air fuel. SA engine is having a homogeneous mixture of air fuel even before entering the cylinder. There is no delay period as such. Supercharging of the engine, it increases the pressure, and increasing the pressure increases the chances of knocking because of the pre-ignition. This delay period can be time taken for the fuel to get burned. Low delay period means that the far away gas mixture will get burned quickly even before the flame starts to reach there. So sudden rise in pressure will be there, so it is not preferred. So actually the answer is increasing the engine speed. Knock in a diesel engine occurs due to instantaneous auto ignition of last part of the charge, reduction of the delay period, delayed burning of the first part of the charge, instantaneous burning of the first part of the charge. So it happens in the first part of the charge, as we have seen. It is due to the ignition lag, which increases the presence of the fuel, and there will be a sudden spike in the pressure and the temperature in the cylinder, and it is due to the delayed burning of the first part of the charge due to the ignition delay, physical as well as chemical delay, ignition delay. The knock-in tendency in the compression ignition engine increases with the increase of coolant water temperature, increase of temperature of inlet air, decrease of compression ratio, increase of compression ratio. So the answer to this problem is decrease of compression ratio. Knock-in tendency in compression ignition engine increases with the decrease in compression ratio. So if the compression ratio is low, temperature and pressure will be low, and fuel will get more and more fuel. More and more fuel will get accumulated. A sufficient temperature is not present for it to vaporize. And suddenly when the temperature increases, all the fuel will start burning immediately, and there will be a sudden spike in pressure and temperature causing detonation. So decrease of compression ratio is the answer. Increase on the temperature of the air will ensure that temperature is high and all the fuel will get burned immediately without resulting in a ignition delay. And increase of coolant water temperature ensures that all the fuel will get the temperature of the mixture will be high, and all the fuel will get vaporized immediately and burned immediately without having a knock-in tendency. So the answer is decrease of compression ratio increases the knock-in tendency in the CA engines. The next is a question regarding the ignition coil setup. So ignition coil is used to step up current, step down current, step up voltage, step up power. So the ignition coil is used to step up voltage from 12-volt battery to 22,000 volts. 1000 volts and supply to spark plug. With the help of a distributor to generate spark. The drive for the diesel fuel feed pump is taken from crankshaft, timing gears, fuel injection camshaft, engine camshaft. The drive for the diesel fuel feed pump is taken from fuel injection camshaft. So in the case of a fuel injection system, camshaft is the cam. It is connected through a roller tappet that is connected to a pressure spindle that is connected to a spring system, plunger spring. And there will be a pressure valve. It is a fuel injection camshaft. The drive for the fuel feed pump is taken from a camshaft. fuel injection camshaft. So this rotation of the camshaft will be rotating the cam, and thereby the roller tappet and the pressure springer and the plunger spring will be operated to allow the fuel to go into the common rail for the injection system. Here there is a similar to this one. There is a suction valve and the fuel intake. So it is the camshaft movement which decides the fuel feed into the cylinder. So it's a fuel injection camshaft which decides the drive for the diesel fuel pump. While following through the rotor blades in an axial flow compressor, the relative velocity of air continuously increases, first increases and then decreases, first decreases and then increases. So the answer is first increases and then decreases. What happens is that in the case of an axial flow compressor, this is a middle drum. There is this rotor blades. Then there is a stator. And the same pattern continues. So as the air passes through the diverging passages between the rotor blades, so as air passes through the diverging section between the rotor blades, its velocity, relative velocity first increases, and then so what happens is that an axial flow compressor compresses its working fluid by first accelerating the fluid and then diffusing it to obtain a pressure increase. So this rotor rotates, imparting kinetic energy and sudden increase in the enthalpy onto the air. And then as it goes through the stator part, this kinetic energy is converted to the pressure energy. So initially there will be an increase in the kinetic energy and then there will be a decrease in the kinetic energy. So the answer is first increases and then decreases. Absolute velocity increases as it goes through the rotor blades. Initially, the absolute velocity increases as it goes through the rotor blades, but rotor will impart work onto the air, and because of that, there will be a bit of a diffusion and increase in pressure, resulting in a sudden, slightly decreased relative velocity at the end of the rotor. So the answer is first increases and then decreases. That solves the problem solving session. Problem solving session 12. In this week, we have seen a few multiple choice questions and numericals based on the lectures we have learned in the previous 12 weeks. And this will these problem solving session will be helping you to solve the problems which will be available in exam, and this will be acting as a guide. And all the best for the exam which will be in the next week. Thank you.